So, I'm Dr. Littman. Call me Mike, Yo Fatty, any of those work. I'm not formal at all. We will be spending 4 hours together for the next 8 weeks. So I would assume by about the 2-hour mark, your minds will be jelly. I know mine is. So in any case, this is 535, which is our first programming course in the graduate program. Now, out of curiosity, how many of you have had some programming before? We assume no programming. So I'll still make it impossible. But we assume you haven't had any. Okay, so nobody's had any programming whatsoever? Minnie, what have you done?
Pascal and DOS.
Pascal, you've dated yourself.
Past Apple days.
Okay, so I take it you haven't written any software in years. That's an accurate statement? And Pascal, so that's putting you in the late 90s when you wrote that?
Late 80s.
Late.
Yeah.
Okay.
Pro-DOS days with Apple.
Oh, okay.
Apple IIs.
Got it. All right. So, it's on the syllabus, but I will put it on here since I haven't put the syllabus up yet. So this is me. You can reach me at my cell phone. Text is probably the best way to get a hold of me. You can call. I probably won't answer. Don't be offended. I do the same thing to my mom. The only person I answer the phone for is my wife because she knows to only call me if it's important. So text me is probably the best way of getting a hold of me. Email. That's probably the second best way of getting a hold of me. Both those ways are pretty legit. I video capture and screen record, or I audio capture and screen record all the lectures, so they'll be up on Angel. So you can, if you miss anything from class, you can put yourself to sleep at night by watching my videos over and over and over again. This probably works at least as well as Netflix. There's also already up on Angel last semester's version of these videos, so if you're really a glutton for punishment, you can listen to me do this stuff twice. Chances are I might say something funny in one of them versus the other, but plenty and plenty of content is out there. Okay, so generally speaking, since grading, and you're probably going to hate me for this. First of all, I completely disagree with the format of this class being an 8-week class. It's a kind of the nature of the beast. You know, a lot of the students in our grad program are non-traditional. Having to compress courses is a necessary evil, but you're going to have a lot of work compressed into a short period of time. So every week you will have a programming assignment. Every week you will have a report, which is, you know, a paper that'll be 3 to 5 pages, something like that. I have already, they're already all up on Angel. So if you wanted to get a head start, or you happen to know you have a busy week one week and something like that, you can work ahead if you'd like. Might be a little bit tough with the programming stuff since I'm going to be introducing the topics as they come, but the report stuff I think you probably could work ahead on if you want to save yourself some time or free up a week in the future. As far as class attendance, I mean, I expect you to always be here, but you know, if you have something more important to do, know that the lectures will be recorded and will be up there. So, you know, not the end of the world. So you'll have every week. So over the period of the course, you'll have 8 programming assignments. You'll have 7 reports. Okay, the final programming assignment is kind of like a final exam-y replacement project-y type thing. And there will also be a written portion to that, but then you'll have a final project that those two things together will go into the final exam. All right, 60% of your grade comes from homework and reports. 40% comes from the exam. Where the exam is, let's say it's 50% written in class and 50% in the form of that final project. All right. Questions, comments, concerns, bribes about any of that? Okay. So, and I'll put the syllabus up that kind of formalizes all this, but this is the gist of it. As far as grading goes, I do give partial credit. I'll kind of go through it here in, well, actually I think I have it up on Angel already. Maybe I wasn't in the right class, because I really thought I had the syllabus up there already. Okay, well, still no syllabus, but I do have their homework directions and self-assessment thing. So here's the scoop. So underneath the Lessons tab on Angel, this little top document here, everybody should read this first thing before you do your first assignment. This kind of gives you an idea on what I expect from the assignments, how to submit things. Basically, any of your programming assignments will be using Java as our teaching language for programming, and we'll talk a lot about that today. And I assume you have never even heard of Java. I give you the whole background rigmarole on it. But when you turn in your programming assignments, I need you to put all your source code into a folder and zip it up and submit that zipped folder. Alternatively, if you really wanted to, you could put all your code inside of a Word document or something like that. I would say the zip folder makes more sense. Worst thing you could do is submit a .java file. So reason is Angel was written in Java, and it thinks all your .java files are executable code and deletes them. So if you submit a .java file, I won't be able to see it. So anyways, this guy explains that. So for your programming assignments, put them in a folder, zip it up, submit the zipped folder. Your papers, Word document, .doc, .docx, or PDF is fine. You know, if you do it on a Mac, I probably can open any format you give me, but stick to those formats so that I can definitely read it like on my iPhone. You know, the papers make good for good bathroom reading material. So, so stick to those. Now, every assignment you submit, whether it's a paper or a program, you need to have this self-assessment form thing that I want you to submit with it. This is specifically important for the programming assignments, but I want you to do it for every assignment. So the scoop is this. So there's 4 questions down here at the bottom. So for every assignment you submit, copy these 4 questions. Paste it into the box in Angel when you submit this, and answer these questions. So for instance, number 1 says, which part of the assignment were you not able to complete fully? For each, explain why you weren't able to complete the part and the steps you took to attempt to complete it. I want to get an idea on what your thought process was. Like I said, this is particularly important in the programming because computer programming is not easy. So I would expect many of you to find the assignments difficult. When you see the solution, it'll always look easier than you were thinking it was going to be when you were working on it. So this allows you to give me some commentary, or you can, I guess, cry to me about how many hours you were spending on it and all that crap, and then I can try to give you some partial credit based on your explanation. Okay, because what we've had happen in the past is students will spend hours on an assignment, turn in nothing because they didn't get it working. Well, I can't do anything with that. So this commentary is very important. So do this for every one of your assignments, even your reports. You know, for the report, I would expect most of the time you're going to say, I think I answered all parts of the report. But so just go through the motions and fill it out. It'll help me zero in on where the problems were in your assignment and also give you partial credit. Sound good? All right. So I think that covers homework and all that stuff. We're starting off here in Unit 1, so the course is broken into 4 units. This is mostly because this course is also offered online, so it has to be delivered in a kind of a more structured way than if it was only a in-person class. So today we're going to have, we usually do about an hour and 45-minute lecture, followed by a break, followed by another hour and 45-minute lecture, and then we're all zombies. So I break it into 2 separate videos, get them uploaded. So again, the videos from last semester are already up here. I will be replacing those with the new ones as they come up, and then I'll probably just put a catch-all link for the fall 2013 videos if you're interested in them or something like that. Sound good? And first homework and first report are already up there. Let me just quickly check to make sure I have unlocked the course to you. I have. So you should all be able to see the Angel course up there. Okay. Any questions about the course in general, how grades will be done, and all that jazz? Go ahead.
Any textbook, recommended textbook?
No textbook. I can recommend a textbook. Like I said, the language we'll be using is Java. I'm going to teach you everything you'll need off my head, and then Google resources would be good. Let's see, is it Title? Yeah, Title Java. Yeah, probably this book is kind of your de facto I'm a student learning Java book. It's written by Harvey Deitel, D-E-I-T-E-L. The newest version, it looks like, is the 8th edition. Go on to eBay or something like that and get like the 4th or 5th or 6th edition for $5. And Java has not changed drastically. So I would not go and spend $80 on a book. I think you can get a used one for $3. Makes sense? Like I said, no required text for the class, but this tends to be the book a lot of beginning programming classes use. You'll hear me in my lectures rip on a lot of the textbooks because I think, especially with Java, they tend to lie to you about some things. So I have fun with that, but that's probably why I don't use a textbook, I guess. Plus, I'm not organized enough to use a textbook. All right, any other questions?
Any deadlines for the assignment submission?
Yeah, each assignment has the deadline of, like, for instance, today I'll be assigning your first programming assignment, which is an easy one, the first one is, and then your first report. They're both due before class starts next week. So, you have the full week to do it. You have access to me during the whole week. Text me whenever you want. I would ask, if it's the first time you're texting me or emailing me, just tell me who you are and what class you're in, because I teach other classes. And most of you I do not know, so I'll have to get to know you. But yeah, feel free to ask for help or anything like that. Anything else? Something pops up, just blurt it out. Like I said, I'm not a very formal person. I don't care if you get up, go to the bathroom during class or something like that. If you get a cell phone call, just go outside with it. I mean, you're not going to offend me. So without further ado, should we jump in? All right. So, what is programming? Can we see the screen fine, or do you want to kill a couple of lights? Or is this good? It's fine? So what's programming? We've all heard of it, right? Okay. What do you think it is? What's your perception of what programming is?
It's a detailed description of unambiguous instructions.
That sounds very formal. I don't disagree.
How to solve a problem.
Okay. How to solve a problem. Instructions for solving a problem. Who are the instructions for? Oh, the computer. Computer, right? Okay, so we all speak natural languages, correct? Some of us, English is our first language. Others, it might be a different language, but we use natural languages to communicate with other human beings. Programming languages are languages used to communicate with a computer. Now, that's what makes programming difficult, is that computers are dumb. Human beings are such wonderful problem solvers that we're so good at solving problems, we've forgotten how we solve problems. I'm going to prove this to you shortly. How many of you, out of curiosity, think you're good at solving problems? Like especially good. How many of you bumped into walls on your way to class today? Walking down the hall, zigzagging, running into any walls? How'd you miss the walls? So none of you hit any walls, right? Well, how did you miss them? Surely you were all thinking about the walls. As you were walking down the hall, you were like, oh, please don't hit a wall today. That crossed all your minds? We don't even think about it. We're so great at solving problems. That's just trivial crap. We don't even think about that stuff. Computers are dumb. When we tell a computer what to do, when we feed it the steps to solve a problem, we have to break it down into the little tiny baby steps to solve those problems. And that's what makes computer programming difficult. It's very difficult for a human being who's so great at solving problems to actually dumb themselves down to the point where they have to think about all the individual steps of solving a problem. Does that kind of make sense? How many of you have seen, I use this in most of my programming classes, how many of you have seen the movie What About Bob? Shocking. This is like the right age group. I mean, I understand when I get my, my 18, 19-year-old freshman.
What's it about?
Okay, Bill Murray. Bill Murray's in it. So is Richard Dreyfuss. And Bill Murray was a kind of a guy who had a lot of social anxiety. And Richard Dreyfuss was a shrink. He's a psychiatrist. So Bill Murray goes to him, and Dreyfuss is, the typical full of himself doctor, has the rich house in the Hamptons, and him and his family are going away on vacation shortly, but he had written this book called Baby Steps. And Bob has problems with everything. This guy can't leave the house for 5 minutes without freaking out. Well, his doctor gives him his book, a signed copy of his book, and the book is called Baby Steps, and it's a matter. So he wants Bob to go through his life taking little tiny baby steps. Don't freak out when you're getting into the elevator. Take one step, followed by another step, followed by another step, to kind of get you through life. Now, Bob has such a success with this that he can't even wait 24 hours for him to tell his psychiatrist about his success. And keep in mind, the psychiatrist is now on vacation with his family, so Bob stalks him. And then the movie gets funny. So, it is a very good movie, and it's a funny movie, but I always reference that because of this baby steps analogy. So now that nobody's seen that? Really? Really? It's a must watch. Killing me. That and Aqua Teen Hunger Force. You have to see both of those things. Who's seen Aqua Teen Hunger Force? We might as well just fail everybody now. All right. So anyways, this idea of taking baby steps, that's the difficulty in learning programming. We're too good at solving problems. Okay, so if we were going to give a concise definition of programming, we might say something like a set of instructions that tell a computer what to do or how to solve a problem or something like that. Okay, so now getting back to this analogy of walking down the hall. So again, all of you assured me that none of you bumped into the wall today as you were coming to class. How did you avoid that? I mean, they're all over the place. I mean, I was walking in, I was listening to one of my audiobooks, I was checking my email, I wasn't even looking up, but somehow I magically missed all the walls. How? So when you walk down the hall, so let's say I'm walking from here to that door. I need to miss all these tables. How am I going to do that? If you were to give me the dumbed down instructions for getting from here to that door without slamming into crap, what would you say? I'm the computer. I'm stupid. You got to break it down for me. How am I going to get over there?
Wide chairs.
Just shove the chairs out of the way?
So many steps this way.
Okay, what's a step? So pretty quickly we could see that it becomes arbitrarily complex. At what point can we stop assuming what I already know how to do? Do I know how to stand? What does standing mean? You know, all the little pieces that go together for us to actually go down the hall without hitting stuff starts with us to be able to go down the hall. And that's complex. When we were like 8 months old, the best we could do is sort of kind of balance then drop on our butt. Now we're texting while avoiding people, moving targets in the hall. We've seen this, right? I've actually done interesting experiments with people texting. I do it first. I text while I'm walking all the time. But have you ever noticed that when somebody's walking and texting, their speed drops by about 30%? Notice this from now on when you see people walking and texting. It's automatic. Their body has to drop down by 30% in order for them to process all the other crap that's going on while they're texting and doing all the other stuff on their computer. I don't know, it's very fascinating. But anyways, in order to tell me all the baby steps that it takes to even get to that door is astronomically complex. Even if I give you some sort of baseline, like this is what I know how to do, because that's what a computer is, right? A computer is the processor. So we think about our computer, we got this thing called the CPU, right? That's the central processing unit. Okay, well, what does that mean? What is a processor besides a couple $100? The brain. Okay, well, what does that even mean? I don't disagree.
Translates.
Okay, translates what?
Whatever language you're putting into it.
Okay. What does your processor know how to do? What does the CPU know how to do? So let's take like our popular processors today are made by Intel, correct? So laptop, desktop, whatever kind of computer you have, it probably has an Intel processor in it, possibly an AMD processor, but it's Intel compatible. So let's just talk about Intel. So this company makes zillions of dollars selling microchips that are Intel processors. Core 2 Duo, Core i7, Core i5, Core i3, whatever. Whatever the latest catchphrase is, right? What makes it a processor?
It gets the instructions and then gives out the output.
Okay. So we give it instructions, but how does it know what to do?
The language, machine learning.
Okay, so is there some baseline? Is there a set of, I usually refer to them as magic tricks? Our processors know how to do a set of magic tricks out of the box. So a processor knows how to do this, 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 and this. And all problems that we solve must be solved in terms of those magic tricks. Okay, that kind of makes sense? All right, so, and the thing is that processors are written in such a way, they're created in such a way that those individual magic tricks are like little tiny widgets. They do a very small task. And you put enough small tasks in a row, you've actually accomplished something more complex, right? So for instance, a command that a processor might understand is something like move AX, BX. That is, move the contents of BX, which is a hardware register, into AX, which is another hardware register. Like, okay, I did that. Well, you do enough things in a row, you might actually accomplish something. Kind of make sense? Okay, so what a processor is a set of talents, a set of magic tricks that a computer knows how to do, that a CPU knows how to do. What's a programming language? A programming language is our means of telling a computer how to solve problems in terms of those magic tricks. And hopefully somewhere in the middle, we can do things that make it easier for a human being to write software, and a computer can translate that into something that makes it easy for it to do. Okay? That's where the dichotomy is. As human beings, we don't really get into this whole zeros and ones crap. We don't have the little 2-digit keyboard and just punching out zeros and ones. We like things to be a little bit more natural language-like. Okay? So, given that, there are 3 types of programming languages. There's machine language, which is zeros and ones. Computers love those. That's definition of digital logic, right? On, off, 0, 1. Computers dig that, humans don't. Then we have low-level languages. Low-level languages have a 1-to-1 relationship with the magic tricks on the CPU. Okay, so every line of code we write in a low-level language translates or is equivalent to exactly one thing that the processor knows how to do. That's the definition of a low-level language. We could almost tolerate that as human beings. If needed, if need be, we could tolerate that. High-level languages. Every line of code translates into many magic tricks on the CPU. That's the kind of thing we like. We like power tools. We like to write a couple of lines of code and have it actually accomplish something. Right? Okay, so those are our 3 types of programming languages. Machine language, low-level language, high-level language. All right. So there are 2 types of programming languages. I got about 6 of these slides in a row that just talk about different types. It's like there are 3 types of programming languages, 2 types of programming languages, blah, blah, blah. There are 2 types of programming languages. We have interpreted languages, and compiled languages. All right, the top level here, we want to think of interpreted as low performance and compiled as high performance. Now, these are all still relative measurements because computers have gotten so fast that the difference between slow and fast may be indistinguishable by a human being. Okay, so this is more of a capability perspective than anything else. So, interpreted languages. These are languages, so let me give you an analogy from real life. Let's say that I'm speaking English to somebody who speaks German. Okay, they don't speak English, I don't speak German. I'm going to need an interpreter in the middle. Okay, so I'm going to speak English to the interpreter. The interpreter is going to understand English but also know German. They're going to translate my English into German and then send it on to the German speaking person. Okay? Now, does the German person get my gist? Whenever I say in English, he's going to understand in German, right? But there was that middleman, so that slowed the whole process down, correct? So interpreted languages work that way, where the programming language is written in one language. The computer understands machine language, or things in terms of those magic tricks. And we have something in the middle, an interpreter, that's going to translate during runtime what the program says to do and then tell the computer how to do it. Okay, so it is lower performance because we are dealing with a translator. We're not speaking directly to the computer, we're speaking to an interpreter. That makes sense? Compiled languages, on the other hand, they work like this. I write out my thoughts in English. I hand it to somebody. They translate it to German. And then whenever it's appropriate, they hand that translation to the German person at the time they need it, and the German person reads it. So it's a real-time, much higher performance. The translation happened outside of runtime. It didn't happen while we were both standing here. I wrote down my thoughts, the person translated it, and whenever the German person needed it, they had instant access to my thoughts in German. Make sense? That's a compiled language. So the act of compiling is translating from a high-level language to a low-level language. That's what it means to compile. And this is right into our wheelhouse for human beings, because we like high-level languages. We like things that are very English-like. We like power tools. So we'd like to write 1 or 2 or 3 or 20 lines of code and have it translate into thousands of instructions that the CPU understands. Okay, but we need the compiler to ultimately turn it into those thousands of instructions. We'll write the 4 or 5 lines of code, let the compiler do all the work of making it this verbose list of instructions to the CPU. Make sense? So that's what the compiler is. All right. There are 3 types of programming languages. We have functional, procedural, and object-oriented. Okay? Now, I'm going to almost entirely gloss over functional. They're a whole different breed. Functional languages solve problems in terms of self-contained functions. If any of you have ever used the Texas Instruments graphing calculator, that's a functional language built in there. So you might solve a problem, you might take the sine of the cosine of the tangent of x, something like that. Okay? Those are functions. Just leave it at that. Functional languages, we solve problems differently. So just know they exist. I'm never going to ask you about them again in here. We are more interested in the other 2. Procedural versus object-oriented. Now, one thing to keep in mind, if we go back to one of the goals of programming, programming has a goal, well, programming languages have a goal of allowing human beings to solve problems on computers in a similar way to how we solve them in real life. That's an important truth. The better the programming language, the more like the way we solve problems in real life is. Okay, so they attempt to mimic the way we solve problems. Now, that comes into the difference between procedural and object-oriented. And really, this is a old-fashioned versus new kid on the block argument. Procedural languages like Pascal are very, when I put it, I'll give some verbiage to it, then we'll talk about it in a much clearer way. They're monolithic in nature and sequential in execution. And I like to give the example using a telephone. So, imagine, if you will, over in my presentation desk over here. Let's say you walked into the classroom and I had a giant pile of wires and crap laying on this desk. Would you believe me if I told you that that's a telephone? Is it possible for me to have a big pile of wires on that table that are all interconnected in all the right ways that it potentially could be a telephone, even though it doesn't look like a telephone? It's possible, right? Okay. You go up, mess with it up for the part, you pick it up, you hear the dial tone, like we have dial tones anymore, right? But you get what I'm saying. A procedural language would look like that. Yes, the telephone's there, but so is all the details. Okay? Human beings like the way we solve problems in real life. When we think of a telephone, a picture pops into our head of what a telephone basically looks like, right? We have the idea of an object that is a telephone. An object-oriented language would have our telephone sitting there on the desk, and it would look like a telephone, with only the public interfaces exposed. Only the things that a human being actually needs to interact with on the phone showing up to us. So we'd have the buttons, we'd have the handset, all that crap, but all the wires, the scary stuff, they're there. But they're inside of the plastic packaging, right? We don't see it, but they're still there. So procedural languages show us all the wires. Object-oriented languages give us a mechanism to hide the wires, to encapsulate them within objects, and only expose the part of the object or the parts of the object that we actually need to interact with. It's not dissimilar to walking into a house with no drywall. In your house, you have drywall on your walls, and all the wires and stuff are behind them. Can you get to those wires if you needed to? Yeah, when there's a will, there's a way. A hammer, a foot, a well-placed butt bump, you're in the wall, right? And you can start messing with the wires. Well, same thing. If I have an actual telephone there and you cared enough to get to the inside of it, could you get inside that phone? Sure. Well, if I had the procedural version of that, everything you need, what you see is what you get. It's all there, including the things that you actually need to interact with. Now, does that mean that object-oriented is better than procedural? Realistically, probably. The reality is that procedural languages only allowed you to accomplish things procedurally. Object-oriented languages allow you to do things in terms of objects, but they also allow you to write things procedurally. In fact, most of our early programs we'll write in here will be procedural programs, but they'll be using a language capable of putting things inside of objects as soon as our stuff gets complex enough where that makes sense. Okay? So questions about those? There are two types of programming languages. We have domain-specific languages, and we have general-purpose languages. Domain-specific programming languages are languages built to solve very specific problems, whereas general-purpose languages are languages built for solving a wide classification of problems. So, domain-specific tend to be smaller languages because they're solving smaller problems. So, for example, HTML would be an example of a domain-specific language. This is hypertext markup language. It's the language of web pages. Okay, and they're solving a very, very, very specific problem. That is, they're solving the problem of formatting text and pictures inside of a web browser. That's it. We're not doing anything else. No flashy anything else. Just make it look good. Another example is SQL. How many of you have heard of SQL? Everybody's heard of it. What is SQL?
Sequential query language.
Okay, structured query language, but whatever, it's fine. So that's what it stands for. What is it?
It's a language to access data, manipulate data.
Okay. So SQL is a domain-specific language for querying relational databases. So it allows us to ask questions of databases. Again, solving a very specific problem. Okay, so those are a couple of examples. General purpose languages solve a general classification of problems. Jack of all trades type thing. So languages here would be, well, here we'll put our Pascal in there. Pascal is general purpose. It's procedural, but it's general purpose. How about COBOL? How many of you have heard of COBOL? How many of you have written anything in COBOL? Does COBOL still exist?
Yes, Lakeland. No, I think Lakeland College teaches.
Oh, teaches it?
Yeah.
Oh, really?
I worked with somebody who had a person.
Like in the 80s or now?
But
That would surprise me. I mean, it's possible that place still teaches it. But yeah, COBOL is a very, very, very old language. My wife is actually a COBOL programmer, which means she's very old. She works where I used to teach at Western Illinois University, so she works remotely now. It's 5 hours from here. But Western Illinois University is one of the few places in the United States, one of the few universities that still writes their own student management stuff. Here on campus, we use Banner. Okay, so we have a product called Banner that somebody else writes, and we just plug it into our stuff. Western Illinois doesn't do that. Whenever they need to change the way student records works or something like that, they have somebody like my wife rewrite a program. Why do they do that? Well, because they've spent thousands and thousands and thousands of dollars and hours writing all these programs the first time, and it's cheaper to just pay people to maintain them than it is to upgrade them all to something new. So they still need these COBOL programmers. Yeah, I don't even know how she does it. It would just boggles the mind how COBOL even exists still. Well, really our big three in here would be Java, C#, Objective-C. How many, well, I already asked, how many of you have heard of Java? Most of us, at least heard of that before. How many of you have heard of C#? How many of you heard of Objective-C? Anybody? Yeah, Objective-C is different than C. Yeah, so we could throw C and C++ into this thing. Objective-C is the Macintosh language. So iPhone programs are written in Objective-C, Mac programs are written in Objective-C. So very Apple specific. Okay, so those are our types of programming languages, domain specific and general purpose. How do human beings solve problems? So this gets back to what we were talking about earlier, where I asked you, how did you get down the hall without slamming into walls? You know, if nothing else, when you come out of this course, you should appreciate how good at problem solving you are. It's so passive for us, we don't even think about it. It's like amazing. This is, and actually within computer science, it's we've heard of artificial intelligence, right? Okay, all the funny movies like Matrix and stuff talk about when we perfect artificial intelligence. All the Terminator movies are the best ones, right? We've all seen Terminator, haven't we? Robot guys come back from the future, kill everybody. Schwarzenegger's one of them, that governor guy. What's up? He'll be back, exactly. Funny, let's see, another movie reference. How many of you have seen Demolition Man? Wesley Snipes is in it. Sandra Bullock is in it. Not old movie, but it's probably somewhere in the maybe mid-90s, something like that. Interesting reference is in that movie they make a joke about something. The premise of the movie is Sylvester Stallone's in it, and the premise is that Sylvester Stallone's they call him the Demolition Man. He's a cop who, he always catches the bad guy, but he ends up destroying buildings along the way. Well, somehow he gets accused of some crime and gets put in cryostasis or whatever, and now we're way in the future, and an old-time criminal has been defrosted. So now they need to defrost an old-time cop to catch an old-time criminal, blah, blah, blah. Well, so Sandra Bullock is like with Sylvester Stallone, like she's the modern-day future cop, and he's the old-time cop who doesn't know the ways of the new world. Well, one of the things that she references is the Schwarzenegger Presidential Library. And it was supposed to be a funny joke back then. Well, I mean, he's already been governor of California. He might change up a couple other laws. You never know. But I don't know why that popped in my head. That was the "we'll be back" thing. That's why. Interesting segues. Well, so anyways, we've heard of artificial intelligence. And all these movies like Terminator and stuff like that, they all talk about what happens when we finally perfect artificial intelligence. How close do you think we are to perfecting artificial intelligence? Not even close. It's as much as we understand so many things in this world, it's amazing how little we understand about the human brain, trying to mimic it. It's really baffling. So I think it will be a very, 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 very long time before if we ever, perfect artificial intelligence. But we've come up with some pretty good ways of faking it. An interesting problem when I was in grad school, we wrote something called the neural network. And it's a simulation. It's a computer program that tries to simulate at a very, very primitive level the human brain. And what we were doing is, we were teaching it math. So we created this neural network. We fed it the 1 through 5's multiplication table. Whenever, and what it did was it would feed the information through and make a guess at what the right answer should be. If it got it wrong, we slap it on the wrist, update some values, keep feeding stuff through. So we kept feeding it the 1 through 5's table and making updates every single time until it got them all right. Basically, until we balanced this neural network to the point where no matter what input we gave it in the 1 through 5's multiplication table, it always got the right answer. Okay? Then we fed it the 6 through 10's table. Data it's never seen before. Got like 98% of them right. It's kind of fascinating because what it did is it didn't learn how to do math. It learned the pattern of math. It's just kind of fascinating thing. So that's kind of like the cool stuff we can do. That and like facial recognition and stuff like that. But I think we're pretty far away from having futuristic cyborgs coming back to kill off people. So maybe one day if we're lucky. Right? All right, so how do human beings solve problems? If we slow ourselves down, we really think about what tools do we use to solve problems. Go ahead.
Reasoning.
Okay. I think that feeds into at least 2 of my 3 things here. It's a little bit broad, but what about memory? How much do we rely on our memory? Who thinks they have a bad memory? But you still remember stuff, right? So some stuff. All the important stuff, I'm sure. So And they make fun of it in some movies and things like that. Back to the movie references, right? But when they've done that in movies or TV shows, when somebody has like short-term memory loss, they make it as if it's a funny thing. But imagine how debilitating that is to not remember things. You know, if you've had friends or family who've had dementia or Alzheimer's or something, I mean, at first it's kind of funny when you see somebody that maybe used to be so sharp and then but it is horrifically debilitating. So could you even imagine not having access to your memory? It's such a basic part of how we solve problems. I mean, I ask you what your name is and you can tell me what your name is. What if you didn't know? Because if you had no facility for storing that kind of information, you wouldn't even be able to tell me your name, your phone number, or how old you are, or where you are. If you don't know where you are, you're going to have a difficult time solving any problems. Okay, so memory is a major, major, major thing for solving problems. Now remember, back to this slide back here, one of the goals of programming is it allows human beings to solve problems on a computer in a similar way to how they solve them in real life. So a programming language has to give us some sort of facility for simulating memory. Okay? So, hello. There we go. Computer programming languages do this through something called variables. Okay? So our concept of memory is simulated through something called variables in computer programming languages. All right, now, next thing is asking questions. What if I said you could remember things, but you're not allowed to ask any questions? Could you actually solve any problems? So going back to our example here of me trying to get from here to that door without ramming into tables and stuff. I have to be able to constantly ask myself, am I about to hit something? Or go back to our example of being out in the hall and not running into the walls. You know, I get myself pointed in a direction down the hall and I start walking. We'll just assume I know what walking means. And constantly, I'm getting inputs through my eyes about what's going on around me. And I have to constantly ask myself a question. Am I about to slam into something? Do I see something in the distance that my current trajectory will make me run into if I don't adjust course? These are things we are constantly having to update. We don't even think about it. We don't count those as questions, right? They happen passively for us. My wife asks a lot of questions. She asks all like the meaningless questions until she gets to the important questions. So I give her a 3-question limit on any topic. Anything you need to know, 3 questions is enough to get to the root of the problem, right? She says, I say she asks too many questions. She says I don't listen enough. So she's right, trust me. Okay, so asking questions is an important way we solve problems. This is accomplished in programming languages through something called conditionals or if statements. Okay, so that's how computer programming languages give us that simulate the way we solve problems through asking questions. Last thing is repetition. So we now know how to remember things. We can ask questions, but we also need to be able to repeat stuff. Because a lot of the things we do to solve problems, we're doing the same thing over and over and over again, right? Like walking. How do you walk? Well, you put one foot in front of the other, start falling forward until you're about to fall down, then you catch yourself, then do it again. Over and over and over again. Stop when you're where you need to be, right? So repetition, and this is accomplished through something called loops in our programming languages. Okay, now we could probably expand on this list and come up with some other things, but I like to break down the way human beings solve problems in these 3 broad categories. We need to be able to remember things, we have to be able to ask questions, and then we need to be able to repeat stuff. If we can simulate those 3 things in a programming language, then we can probably solve a pretty good generalistic set of problems. Having said that, something I hear from juniors and seniors in undergrad all the time is like, oh, well, you know, I'm not good at this language, but I'm really good at this language. I mean, this is just stupid. You know, all programming languages are the same. You know, with very few exceptions. If you came up to a language, if you taught yourself how to do memory, how to do variables in it, how to ask questions, and how to do loops, you could pretty quickly get up to speed in that language. So saying one language is easier than another language doesn't make a whole lot of sense when you've been exposed to both. I mean, obviously, you know, like in natural languages, you know, like I don't know Russian. To me, the Cyrillic alphabet seems impossible. So I'm not exposed to that, so obviously I would say, well, I'm better at English than I am at Russian. Definitely a true statement. But had I learned both, I would think that they would both have many, many, many similarities. Okay, so questions about this stuff. All right. There are two kinds of programming languages. We have loosely typed and we have strongly typed programming languages. And this involves the concept of variables, which is why I did it after we talked about variables, at least at the high level. A loosely typed language. Let's say you go to Target and you buy one of those giant Tupperware things, you know, to store crap in, right? A loosely typed language would say we have some Tupperware, we could store anything we want in there. So I can put shoes in there now, and then in 3 weeks I maybe empty the shoes out and throw them away, and I can put clothes in there. No big deal, right? That's how a loosely typed language would work, just generally speaking. Strongly typed languages, though, when I buy that Tupperware, I have to label it shoes. And that's all I can ever put in there is shoes. If I want to put clothes in there, no, I got to burn it. Go get it. I got to go out to Target, buy a new one to put clothes in. Label it, clothes. Okay, well, which sounds better? Well, from a human problem-solving perspective, well, I kind of like to put whatever the heck I want in the buckets, right? That's true, but these have some connotations as it relates to programming. Loosely typed languages generally are considered lower performance languages. So these are languages where we can define a variable, define a space in memory, without telling it what we intend to store there. Okay? Strongly typed languages, we can generally say, are higher performance languages. These are languages that when we define a place in memory to store something, we must tell it what kind of value it's built to hold. Now, the reason that's higher performance is because it has to do with when the work is done. In a strongly typed language, it's up to us, the programmer, when we define a variable to say, this guy is built for holding integers, or characters, or strings. So we're doing it way ahead of time. All right? So it's only costing us, the human being, time during the time we're programming it. But when the program is actually running, it knows what kind of values are in a particular variable. There's no extra work that has to go into figuring that out. In a loosely typed language, the programmer's not responsible for saying what kind of value gets stored in here. Instead, at runtime, there's this extra guy that's running alongside your program. These are usually, the term for this is something called a type inference engine. I'm a big, I don't know, advocate? Yeah, maybe advocate is the right word. You know how in really almost anything higher ed, but technology specifically, we have all these like really scary sounding words that mean easy things. You you go to Best Buy and just throw keywords out there, right? Just buzzwords, and they're supposed to make them sound smarter or something like that, It's like, oh yeah, we have this 14 trillion gigabit flip-flop hard drive thingy-majiggy, and they're meant to sound all fancy, I guess. Same thing here, inference engine. Type inference engine. We just throw the word engine on the end of it, and it's supposed to sound complex. It's a computer program that sits there and has to and its job is to figure out what's inside of a variable. That's all it does. Well, that takes time. It's slow because that's happening during runtime. We can't just immediately say, okay, I'm going to add 5 plus whatever's in this variable, because what's in that variable very well might be an ice cream cone. And 5 plus an ice cream cone doesn't make sense. If it's a number, now we can do some math. Well, in a loosely typed language, we have to wait for the type inference engine to come back and say, yeah, this guy's mathable. You can do some math with him. As opposed to a strongly typed language where we wouldn't even be adding if it wasn't already of type integer or something like that. All right? So those are our two types of programming languages, loosely typed and strongly typed. Let's talk about Java. Java is a high-level, object-oriented, general-purpose, strongly typed, compiled language. Did I cover all of our different types there? Got the high level, got the compiled, got the object-oriented, got the general purpose, got the strongly typed. Okay, I think we're good. So, that's where Java lives in the world, as does C# and Objective-C, our big three. They live there. If we go back here just for a second and throw a couple of example languages into some of these, some examples of loosely typed languages, just more for trivia than anything else. PHP is a loosely typed language, and so is a language called JavaScript. JavaScript and Java, not the same thing. They just happen to share that those 4 letters. Okay? So those are our loosely typed languages. Well, there's more than that, but those would be examples. How many of you have heard of PHP? I think most of you probably have heard of it before. It's a web programming language. It's probably not uncommon for you to have gone to a web page where the page you were on was, something.php at the top instead of .html. So it's a common web programming language. Strongly typed languages, well, we got Java, C#, Objective-C, C++. Really a lot of languages are strongly typed. Many more languages are strongly typed than loosely typed. Actually, that may not necessarily be a truth. Many more common programming languages are strongly typed than loosely typed. I guess if you take the collection of all languages that have ever been created in the history of programming languages, it might be balanced a little differently. Domain specific, we gave some examples there already. Let me give a couple of examples here of functional, examples of functional languages. We have a language called Lisp, Scheme, Prolog. Those are functional languages. Interestingly, all 3 of those languages are in the field of artificial intelligence. Procedural languages, we have Pascal, COBOL, C, not C++, but C. Good enough. Object-oriented, we'd have Java, C#, C++. So C++ is the object-oriented version of C. We'll talk a little bit more about that here in a few minutes. Some examples of interpreted languages. Scheme is interpreted, Lisp is interpreted, PHP is interpreted, JavaScript is interpreted. So again, notice that these things go along with low performance. PHP is considered a low performance language, even though it's probably the most popular web programming language today. The trade-off is, because it's being low performance, it's an interpreted language. It's also, which means it's not a compiled language, which means that changing the contents of a web page can happen very quickly. So you don't need to make a change, then recompile it, then upload the recompiled version. You just have to go in and change the code and save it, because every time the program runs, it's interpreted on the fly. Okay? But again, this goes back to something I said a while ago, where our computers have gotten so quick that the difference between low performance and high performance for most things is indistinguishable. All right, compiled languages, Java, C#, Objective-C, Pascal, C++, C. Those are compiled languages. All right, and then here at this first slide, machine language, zeros and ones. I can't go any lower than that. Examples of zeros and ones is zeros and ones. Low-level languages would be like assembly language, and we'll talk about this here in a few minutes. I'm just kind of filling in some of the gaps here before we start talking about Java in a lot more detail. Okay, so we have assembly language is a low-level language. High-level languages, Java, C++, C#, Objective-C, so on and so forth. And if you go through these, you should start seeing a pattern. That we have our high-level languages. These are the languages humans like using. The compiled ones seem to have a lot in common with those. The object-oriented ones seem to have a lot in common with those, modern ones. The procedural ones have a lot in common with some of the older ones of those. General purpose, again, have a lot in common with the stuff that, so a lot of these lists share the same programming languages. All right. So, back to Java. So Java is a high-level, object-oriented, general-purpose, strongly typed, compiled language, as is C# and Objective-C, our big three. Java is most famous for being something called platform independent. Platform independence means that you write the program once and it will run on any platform. Well, let's talk about this in context. For starters, let me give you a little bit of a hierarchical history of where these languages came from. So at the top of this list, I'm going to put the C programming language. I'm going to put C at the top of the tree. C is a procedural, high-level, general-purpose, compiled programming language, strongly typed programming language. All right? And it is the grandparent, great-great-grandparent of our modern languages. and it's procedural. Now, from C, they decided, hey, we need object-oriented C. So they created a language called C++. Before that, programmers started faking it in C through something called structs. And when we get to the point in Java when we start talking about objects, I'll kind of dive back into that, but just trivia for right now. Now, what was happening back during this time? How many of you heard of Microsoft? All of us, right? How many of you have heard of Apple? They all like each other, right? All right, so when C expanded to C++, and that's what Microsoft was using, Apple said, we like C too. They were both using C. But we're not going to jump ship to C++. Instead, we're going to create a language called Objective-C. Da, da, da. All right. Now, from C++, which is a extremely popular language. In fact, probably still the most popular game programming language. From this, we migrated to Java, and C#. And I'm going to tell this story here in a little bit. That's an interesting story. And what did Apple do? They migrated from Objective-C to Objective-C . Highly inventive. You got to keep in mind, this was back in the days when Apple wasn't that inventive with their software names. You know, like for the first many Macintosh operating systems, it was Mac OS 5, Mac OS 6, Mac OS 7, Mac OS 8, Mac OS 9. Highly inventive, right? At least then they started going to jungle cats. So they had Mac OS 10 was the first one. Panther. We had lion in there. We had tiger and mountain lion, and they finally ran out of cats. It's actually funny. This last year I was at. They just came out with the newest version. I'm running it here of Mac OS X, OS 10, which is called Mavericks. They ran out of cats. That's what happened. So now they switched over to something else. And so Apple made a little kind of a joking presentation when they were kind of announcing their the new operating system, that it was coming, not the day it was coming out, but that, it's in beta right now. It'll be out in a year or something like that. And Apple said, we're starting to run out of cats. So, we started thinking, well, maybe can we do a play on it? Because, we had lion, then you had mountain lion. So then they had, how about OS X sea lion? And then they put a picture of a sea lion there. And it was kind of funny. So only recently has Apple gotten a little bit more inventive with names of things. They're still pretty boring with the iOS for the iPhone. We have, iOS 1, iOS 2, iOS 3. They just had the most innovative one, iOS 7, just came out. Boring. Why don't they use, iOS Gerbil or something like that? Android's interesting, right? How many of you are Android users? Versus, how many of you are iPhone users? See, at least, what's this?
How many of us are still flip phone users?
Are you serious?
I am serious.
Oh my gosh, how do you function? I recently spent 10 days with a flip phone user. He's my blind deaf grandpa who's 83. And they shouldn't let him have the phone because he can't see, which makes it bad enough for dialing, but he also can't hear. So he calls people, but he doesn't know what you're saying. But he's happy. I mean, oh my gosh, he's laughing the whole time. He calls the grandkids, and most of them can't speak because they're little babies. Well, I mean, great grandkids. He calls the great grandkids. Not the I'm a grandkid, but yeah. So him and them, they communicate. They're babbling on the phone. He's babbling on the phone. And yeah, so it works out well, I guess. But they were amazed because I had my iPhone there and I was showing them FaceTime. So I FaceTime with my brother, so my grandma and grandpa could see Miles, my brother's 2-year-old. Oh, they thought that was the best thing since sliced bread. That, oh, wow, there's a human being moving on the screen. I don't know. Okay, so anyways, I was saying Android. Those of you who are Android users, they at least have interesting names for their operating systems, right? Ice cream sandwich. Jelly bean, right? Come on, Apple. Get with the program, right? I mean, I'm an iPhone fan, so I mean, I think iPhone makes the superior product, but not because Android is bad. Android's made by Google, and Google is solving the old Microsoft problem. So this kind of segues into some of our discussion here. Google is writing a single piece of software, Android, for 1,000 different phones, right? Apple is writing iOS for their own hardware. They control both sides of the coin. I mean, no wonder it just kind of works because they don't have to worry about other people's hardware messing their stuff up. So when you really think about it, Android is shockingly good, just like Windows. I mean, people complain that, oh, well, Microsoft Windows is buggy, it's crap, whatever, blah, blah, blah. Well, it's running on 94% of all desktops. They got a couple of users. Those people who say the Mac operating system is better, fine. I mean, I'm with you. I'm a big Mac user, but you know what? No wonder the Mac operating system works pretty well because they're designing it for their own hardware. Microsoft's not. They're writing this one program for a zillion different computers. All right, so that kind of gets us back to this thing of platform independence. So we use it to segue a little bit. Now, we had a problem. Let's talk about video games. I'm sure we're all big gamers, especially Flip Phone over here. Big. kind of a big into Halo. So we have an issue. So you don't have to know anything about video games to follow this. This is more of a instructive type thing. For those of you who, and this is most apparent on computer gaming, rather than the console games like PlayStation and Xbox, those things. But so let's say that you were a PC gamer and you have both a Mac and a PC. Okay, a Mac and a Windows machine. When a new game comes out, more than likely it's coming out for Windows, right? Biggest market. If you're writing a video game, you're going to make more dollars off the 94% of the people than the 5% of the people, with the last 1% being like Linux and Unix users. So in any case, most of our video games are written in C++. Maybe more recently, some of them written in C#, but most of them are C++, especially if they have any sort of inkling that they'd like to be ported over to the Macintosh at some point. Now, the general way things worked is a game would come out for Windows, and if it were to ever come out for the Mac, it would come out 6 months later, something like that. The reason for that is they'd write the program in C++, compile it for the Intel architecture on Windows, but they couldn't just go and compile it again for the architecture on Macintosh because there was some software incompatibilities. The biggest one is something called Directx. Directx is Microsoft's 3D polygon graphics system. pretty pictures and colors and crap like that on the screen. That's Microsoft's technology for it, which is Windows only. Well, since Macintosh is not Windows, it doesn't get DirectX. They use something called OpenGL, which is a competitor product. So we can call them relative equivalents. Now, the easy thing to do, if you were a game developer, to save yourself a bunch of headache, is to just do everything in OpenGL, because OpenGL also runs on Windows. But Microsoft has been known to be somewhat proprietary and maybe put some words out in the street that you should use DirectX or else type thing. So most games written for Windows are written in DirectX. And in some ways, DirectX is the higher performance platform. In other ways, OpenGL is higher performance. But it's regardless, it's a trade-off. And this is all just part of the example here. Point being that if I were to write a video game in C++ for Windows, a large portion of that game, that is the portion of the game that makes stuff look pretty and awesome on the screen, is going to be written in something that's different than what would be compatible with the Mac. So if I want to then turn around and release my game on the Mac, I have to go and rewrite probably a major portion of that software to cover the new way of showing stuff on the screen on the Mac. Now, that's kind of the most obvious example. Even outside of that, even if we just had like a business application that wasn't using tons and tons of graphics or something, there would still be incompatibilities between the two platforms. You might have to go back and rewrite portions of your program to work differently on the Mac than you did on the PC. Concept being that if you wrote something in C++ for Windows, if you wanted to have it run on the Mac, you'd have to basically write it again. Maybe 80% of it again in order to make it work on something else. Okay? Well, that's problematic, at least in some examples, right? If you're somebody who's selling video games, maybe not the end of the world. If you're a real computer gamer, you own a PC. That's just the way it works. I don't think most game companies are all that concerned about alienating the Mac users. Especially not today, because I can install Windows on my Mac and I can run all the Mac games, or all the Windows games on the same machine. But in any case, one of the big selling points for Java, which was announced probably in 1995-ish, I think is when Java probably first started coming on the scene, is that it was platform independent. And what that meant is you wrote your Java program once and it ran on every platform. It ran on Windows, it ran on Mac, it ran on Unix, it ran on Linux. You write it once, it runs on everything. That sounds awesome, right? Sort of. Here's the catch. I'm going to draw some more pictures. So let's start off with a C++ example. So we have our C++ source code. We compile it. Once it compiles, what is compiling? What does it mean to compile something? Translate it from what? What kind of language to what kind of language? Yep, high level to low level. So we're going to take our high level C++ source code. We're going to send it into the compiler, and it's going to come out on the other side as a low level language. So probably x86 assembly. Okay? So we converted from high-level C++ code into x86 assembly code, which then ran natively, on the Intel CPU. And actually, I'm going to add one more layer here, just for completeness. So then which ran natively in Windows on top of the Intel CPU. So this was the life cycle of a video game written in C++. Similarly, that same game written in C++ for the Mac, we compile it. I'm just going to date the Macintosh architecture a little bit just so these look very different. Macintosh is all run with Intel-based processors now, but go back 8 years ago or something, and they were running PowerPC processors, which is a different architecture. They ended up losing in the desktop market. They're a RISC-based processor, a reduced instruction set. So Intel's architecture won out there, but actually reduced instruction sets making a strong comeback on the smartphones. So most of our mobile devices are running on something called an ARM processor, which are all reduced instruction set things. So, but in any case, they failed out on the desktop, so this guy no longer exists. But he did on PowerPC-based Mac, so I'm going to just use that as my example here. So we take our same game, probably with some modifications. We had to probably rewrite 80% of the code. Compiled it down to RISC assembly. It ran on the Mac on the PowerPC CPU, let's say. Okay? So here would be an example of a language that was not platform independent. We had to write the game twice in order for it to run on 2 different platforms. Make sense? Okay. So let's look at how Java works. So we're going to take our Java source code. We're going to compile it. It's going to compile down to something called Java Bytecode, which is a low-level language. So just like x86 assembly is a low-level language, and RISC assembly is a low-level language, Java Bytecode is a low-level language. That is, it has a one-to-one relationship with the processor it runs on. Okay? Now here's where things get weird. Because again, Java is platform independent. This Java bytecode is a low-level language which has a one-to-one relationship with the CPU in which it was built to run on. The problem is it was built to run on something called the Java Virtual Machine, JVM. Maybe you've seen this in an error message at some point, JVM or something like that. So this is the Java Virtual Machine. What is the Java Virtual Machine? It is a computer written in software. The Java Virtual Machine then interprets for Windows on an Intel CPU. I'm just compressing. All right. Now, what's nice about this, again, Java is platform independent, which means that I can take this piece one Java program that we compile down to Java bytecode, which is a intermediate language, which is a low-level language that is understood by the Java virtual machine. So what they did, the people from Sun Microsystems, so going back to the Java slide, Java was made by a company called Sun Microsystems. What they did is, rather than forcing the programmer to write their program 3 different times, Sun Microsystems wrote the Java virtual machine 3 different times. They wrote a Java virtual machine for Windows. They wrote a Java virtual machine for the Mac. They wrote one for Unix. They wrote one for Linux. They wrote one for Solaris. All these different, random flavors of Unix. So they ported their software, the virtual machine, to all the different platforms. And the virtual machine knew how to run Java bytecode on that particular platform. So if I take this program that I compiled once and I run it on a Windows machine or a Linux machine, it'll run through the Java virtual machine that was written for Linux, which gets interpreted for Linux onto the Intel CPU or whatever CPU is on there. This Java virtual machine, which they wrote for Windows, would interpret for Windows on an Intel CPU. This virtual machine, which they wrote for Macintosh, would interpret for Mac on whatever CPU. All right, so the idea is that we don't have to write our programs multiple times. Sun Microsystems instead wrote our virtual machine multiple times for every machine that they intended Java to run on, every architecture they intended Java to run on. But we go back here to this slide, we see that Java is a compiled language. That's only a most truth, mostly true, whatever. Because we see a step here where things are being interpreted. See that? Yes, we compile Java up here, down to this Java bytecode. This would usually be called something called an intermediate language. Yes, it's a low-level language, but we call it an intermediate language because what's right here and what's feeding into Windows are not the same thing. So this is an intermediate step before we get to the actual final language. All right, so at some point, Java is also an interpreted language. So at runtime, we're feeding this Java bytecode into the Java virtual machine, which is a computer program. So the Java virtual machine is a computer written in software. And that computer program is then taking that Java bytecode and interpreting it into native code for that particular architecture, whether it's Windows or Linux or Mac or whatever. Okay? Now, this is ingenious from the perspective of, hey, I'm a programmer, I only want to have to write my software once. But the idea of platform independence, like we have talked about over here, still relies on performance. Now, those of you who do play video games, we want our games to be fast, right? Are we going to put up with second-rate crap just because the programmers behind the scenes didn't have to work as hard? We don't want that. So, you don't see any video games being written in Java. It's not high enough performance for true video games. You might see like the online poker, those kind of games. That doesn't require any sort of crazy stuff, so that might be written in Java. But you wouldn't see Battlefield written in Java or Halo or anything with lots of explosions. Okay, these are games that are very, very, very streamlined. So does that mean Java doesn't have a place in the world? No, Java is actually highly successful. In fact, probably where it's most successful is in business applications. Like I said before, our computers today are so fast. For most applications, we're not going to notice this interpreting step. Java's plenty fast for, let's call it, 98% of all applications. It's those high-end video games, one specific genre of software, that it's really not the appropriate tool. Okay? Now, it's a very lucrative area of technology, so that can't be ignored, but so are business applications. In fact, Java has really thrived. How many of you have ever used a stock trading platform like E-Trade or Thinkorswim or anything like that? So something that's cool with these, and this is really probably an industry where Java's really excelled. Let's say that you decided that you watched some webinar or something, you're going to be a day trader, some high power stock trader or something. You go onto a platform like Thinkorswim or E-Trade, and they'll, for only like $100 a month or whatever, they'll sell you their professional software package for the true power broker or whatever. And what is it? It's a Java program that launches out of your web browser. But it's a full-fledged, high-performance application for doing real-time stock trading. It's not a video game, though. So where it's plenty fast for real-time transactions, it's not plenty fast for real-time explosions and robots coming back from the future to kill people. Okay, so Java's actually found a very good place in the world, and this platform independence makes a whole lot of sense because now people can go out, let's say you're a business person, you can go out and get a machine that you like rather than the machine that your software runs on. Kind of make sense? So if I'm a stock trader, I don't have to worry about, does E-Trade support Windows or Mac? Because since they're using Java, it works on both. Make sense? Okay, so that's kind of the Java story from a platform independence perspective. Now, let's tell the Microsoft story real quick, and then we'll take a break. All right. So today's headline: Microsoft stole Java. Now, what's interesting about this? First of all, I'm a big Microsoft fan. Also a big Apple fan. I'm a big technology fan. The world of computing today would not be where it's at without people like Steve Jobs and Bill Gates. And these people are lunatics. But I think to change the world as much as they did, you need to be off your rocker a little bit. So one thing I want to defend Microsoft a little bit on this. First of all, this one bit them in the butt. They stole from the wrong people. But generally, Microsoft's business practices, as it is with a lot of big companies, is they will go out and take what they want. If there's a technology out there that they want, they'll go and take it. Then they'll get sued, and then they'll settle outside of court for some gigantic amount of money. Now, is that wrong? Let's say that I'm a computer programmer. I invented something, came up with some interesting software that Microsoft got wind of and decided they wanted to steal it from me. Chances are I didn't have the means that a company like Microsoft has to really make my software successful, right? Isn't it actually good for me that Microsoft steals it, I sue them, and they settle with me for $50 million outside of court? That's like a good thing, right? Take your 50 mil, go retire. That's also good for Microsoft. Microsoft's other option would be to come and try to acquire my technology. So Microsoft comes in, there's a negotiating phase, and I go and get a lawyer, and they have their team of lawyers, and we go back and forth for 3 or 4 months or whatever, however long it takes, and finally settle on some number that's probably less than 50 million. Probably less than what I'm going to sue them for, if they just stole it from me, right? So I didn't benefit in this, and neither did Microsoft. So our laws allow for Microsoft to just take what they want, have me scream about it, sue them, then they give me a big wad of cash. And the world just keeps turning. Okay, so I don't necessarily want to paint Microsoft into a bad picture with this headline. In fact, actually in this one, they got reamed pretty good, Microsoft. Like I said, they stole from the wrong people. But generally speaking, that is how technology works anymore. When you see these acquisitions that show up on the news and things like that, typically those are from friendly vendors. Like when Apple acquires company XYZ or something like that, that's probably something where Apple's been partners with them for a while for some technology. This is what happened with Siri for iPhone. Apple was working with another company that did the technology behind Siri, and Apple just ended up buying the company. Made perfect sense, right? As long as somebody's getting paid. So anyways, the makers of Java was a company named Sun Microsystems. How many of you have heard of Sun Microsystems? Okay. They no longer exist. They're now called Oracle. Okay. Also a big company. Okay. Sun Microsystems was not a slouch. Okay. This isn't some kid writing software out of their basement. This was a major software company and hardware company. They created... They were huge in the networking space. In fact, in the IT industry, you may still go into universities or enterprises that are still running Sun servers, running their Solaris Unix-based operating system. So this is a major company, okay? Well, they came out with Java. And we just kind of went through the motions here and talked about this concept of platform independence. Is it as good as it sounds? Well, in some cases, yes, but not in all cases. But still, pretty cool innovation, right? Well, Microsoft decided, hey, we like that. So what do? Well, Microsoft had a product called Visual Studio. They still have this product called Visual Studio. Visual Studio is something called an IDE. Integrated Development Environment. We will be using an IDE in here called Eclipse for Java. We'll talk more about that later, but that's what Visual Studio is. It's a integrated development environment for the Microsoft suite of languages. And within Visual Studio, they released their next release of Visual Studio in this time period came with a language called J++. And what was J++? Well, it was Java syntax, but in Microsoft's IDE. That part's not a problem. Okay, it's not a big deal to have Microsoft's IDE supporting Java. But Microsoft's IDE was not supporting Java. They were supporting a brand new language called J++, which just happened to be Java. Okay, so Microsoft decided, we like Java. We like Java syntax. Java Virtual Machine runs on our platform. Well, we're just going to take their language and build it into our product and start selling it, which is actually funny because Sun, go back here to, where's my Java slide? Made by Sun Microsystems. Sun's ticker symbol on the stock market was Java. They banked on Java being kind of the money maker for their company. Now, what's interesting is they never actually found a way to monetize Java. Java is at the core of so many technologies that we use today and that we use then. But Sun, because of the way they distributed Java, it didn't cost anything. If I wanted to use J++, I had to go out and spend $300 on Visual Studio. You know, if I wanted to use Java, I went to Sun's website and downloaded it for free, legally. They were just giving it away. In fact, Sun even had their own IDE that you could download, also for free, called NetBeans. If you're a developer writing in Java, why not charge $100 for this? Especially back then. I mean, now we're not accustomed to paying for things anymore. We just steal it. So it's a whole different world now, I guess. So, but I mean, I obviously don't know the economics behind this, but it's clear that a big weakness of Sun Microsystems was that they never found a way to monetize Java. Part of that was probably an early push to make Java popular, which it did. They made it popular by making it easy for people to get it. It was free. It did a lot of good stuff. It used a syntax that was very similar to C++, which was already highly, highly popular. Okay, so it wasn't like learning a brand new language. It was like, you know, learning English and then going to Texas and learning the English they speak there. You know, basically the same thing with a couple of extra little slangs thrown in there, right? Okay, so Java versus C++, very much like that. So they leveraged a group of existing programmers who basically already knew the language. They didn't charge them anything, and they got people excited behind this whole platform independence idea. Good, 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 right? Java took off. Sun Microsystems didn't make any money off of it. A lot of notoriety, but no money. So, anyways, Microsoft comes out with Visual Studio, and one of the language packaged in there was J++. They also had C++ and Visual Basic, and I think at the time they might have had Delphi with it, which is Pascal, Visual Delphi. But in any case, J++ was one of the languages. Well, this kind of ticked Sun Microsystems off. And they weren't the kid writing the software in their basement who would be happy if they could sue Microsoft and just get a settlement. No, Sun Microsystems wanted Microsoft to not pay. They wanted them to give up, not use their product. So they went and sued Microsoft, and Microsoft lost and was not allowed to have J++. They had to pull it off the market and pay some hefty fines. So Sun got money and then also won the rights to their software. Not many people could successfully fight Microsoft in court like that. But Sun is not a slouch company. So anyways, Microsoft still liked this idea. Like, you know, this idea of platform independence, I like that. But maybe we can do a little bit better. So they went to work on something called C#. C# was a brand new language built from the ground up. This is all according to Microsoft. I was at a ACM conference at the University of Illinois in Urbana-Champaign. This must have been in 2000. Well, maybe earlier than that, maybe 99. Somewhere between 1999 and 2001. Somewhere in that range. This is when Microsoft was first announcing that they were working on C#. And everybody when you go to these conferences, you always got to go to Microsoft's presentations because they give away the best free crap. They were giving away Visual Studio Professional box software. That's a $600 software package, which we immediately put on eBay. Because we had all stolen it, right? Downloaded it. What do you need that for? Okay, so, you know, in any case, you know, by the way, don't do that. Especially, I think there's an ethics course you guys have to take. You don't steal software. In any case, you always got to go to Microsoft's things because they give away the best free crap. So I'm sitting in the front row and I'm listening to this guy talk about C#, and I was a big Java programmer at the time. And he's like, oh yeah, so we have this language. We built it from the ground up, earth-shattering. Nobody's ever done. This guy basically described Java. And even today, when you write, if you took the traditional Hello World program in Java and tried to compile it in C#, you would have to make less than 3 changes for it to work. But the syntax was different, ever so slightly, but different. Keeping in mind that there was already a precedent for that because Java used basically C++ syntax. So there's a good reason to use very similar syntaxes because you want it to be something that's already familiar to the programmers you hope to adopt it, right? So the only thing they didn't do is use exactly Java syntax. And they also didn't use exactly Java technology. They couldn't use a Java virtual machine. They had to write their own equivalent, if you will. Okay? So this whole lawsuit forced Microsoft to come up with a language called C#. Now, what I'm going to do here is let's take about a 15-minute break, come back at 8:15, and we're going to start up the conversation by talking about how C# differs from Java. Sound good? All right, and I'll stop this recording and get this one uploaded.